There is a sentence that I love in presentations and in particular in technical conferences, which I always promise myself to do not say, but I say it because of Ruud. And it says, in the interest of time, I will welcome Dr. Anders Ruud van der Paan. a great friend. So you will introduce yourself and say a few things about us.
No, actually, I'm not going to introduce myself. I want to spend time on more useful things, like my slides. And thanks, Nicholas. There's a time and place for everything, and I would call this time suboptimal for my biorhythm, but I can tell that it's different for you, so that's really great. I didn't expect this kind of turnout at this time of the day. I put together a fairly basic presentation, but as it turns out, by the way, my slides are not online yet, because it's like quantum physics. They're only real once you've seen them. So that's actually the truth, because they've kept on changing them.
I don't not to worry. He has a sense of humor.
No,
You would judge.
No. We have to be very serious in that. So this is going to be a very basic talk on NUMA, and for people that already know it, I apologize. I think there's still coffee out there. There's also decaf, but they call it hot water here. And it's going to fit in with what Dan said, but that's going to be at the very end, of course. So let's get started. I should be able to finish on time if this thing is going to help me.
Just click on your slide to get this.
Yeah, we'll just do it like this. What's NUMA? Well, this is why we have NUMA. This is not NUMA. But this is why. I was there, I was around when this architecture came out, the good old symmetric multiprocessor SMP. And it was a beautiful system. It had like a flat memory. Everything was very simple. It behaved like a large workstation, all fine and good. But it didn't scale well. And I saw that with my own eyes. I was at SDI at the time. And SDI had a system called Power Challenge. And they were working on a new system. But the new system took a little bit longer. The processor division had already produced a processor that was ready. The system wasn't ready. So some brilliant blight decided, you know what, we'll just stick those processors into this design. And guess what? There was hardly any benefit because the interconnect was your bottleneck. It already was tight with the current processors. You'd stick in a faster one, and you hardly saw any benefit. But it was like a stopgap solution to what later was going to be the origin. So this has a scalability bottleneck because that bus interconnect or whatever you have has a fixed bandwidth, and you'll starve your applications. And that led to the creation of NUMA. NUMA stands for non-uniform memory access. So I have that. And I hate asking questions to the audience just when I'm about to doze off or check my email. There's a question asked, and I usually don't even get the question because I need time to wake up. So I'm going to do this. If you want to pitch in the next slide, that'll be fine. But what's NUMA? It's a great way to get more scalable memory performance. So the computer architect will say. Developer will say, I got no clue what you're talking about. I've never heard about NUMA until you just mentioned that word. The performance analyst will basically say, it's a pain. My question to you is, who's right? So let's do a bit of show of hands. Let's wake everybody up. Let's do that. Who thinks the first one is right? Come on. Yeah. How about the second one? How about the third? Yeah, you could all kept up your hands all the time because they're all right. They're all correct. That's the misleading thing about NUMA. It is really nice from a certain distance, but when you get into the ugly dungeon, it gets really, really difficult. Actually, I was very glad to see on the agenda that one of the talks today is by you about different ways of doing memory, and that's very near to me. So who knows? Maybe there's hope. So what is a NUMA system? And I'm showing you a generic system, but it's kind of like a template of many things that are out there. It starts with a node, and the node is like that good old SMP. And these days we talk about cores, but it has a flat memory at this level. Memory access time is the same. And then what you're going to do, you're going to take multiple of those nodes and you're going to glue them together. If you glue them together through a regular network like Ethernet, you talk about a cluster. But in a NUMA system, there's a cache-coherent interconnect. Cache-coherence basically means that you get visibility in the entire system. Whenever a change is made, you'll see it at some point. And that makes it really nice to program. So this system behaves like a single system image, where you ask a tool like top, it'll tell you this many cores you have, this is the memory you have. It doesn't show you the underlying topology. And the reason to do this is scalable bandwidth. Because each time you add a node, you add bandwidth to memory. But there's always a price to pay. And in this case, the price to pay is that you fragment your memory, you make it non-uniform. So with NUMA, memory is physically distributed, but logically shared. To you, this is one memory. The shared data is accessible by all threads. The thing is, you don't know where the data is, and it doesn't matter unless you care about performance. Then it does matter. So this is like the simplified high-level view. I have my NUMA system, and I have my thread executing somewhere in that system. Now, I need memory, and it can be two cases. It's local, that's the fastest you can get. You just grab whatever you need from the memory you're connected to. You can't get any better than that, you can't get any faster than that. But why not this? Because the system is hiding the topology for you, and your data may end up in a faraway corner of the system. You'll still get it. So to you, all is well. You need some variable, you'll get it. It just takes longer. And that's why in the NUMA architecture, you have a notion of local and remote. Now, you can go into the numbers and how many nanoseconds that is. It doesn't matter. It's always going to be slower. It's the difference between fast and slow. So that brings me to the main goal of NUMA, tuning for NUMA. You want to avoid that second situation. You want to keep your data and your threads close. That's the whole idea. And I try to avoid this slide, but I found out I need it. I need to talk a little bit about what's called hardware threads, because I need it at the end of the talk. Some designs, in addition to the core doing all the computational work, you have what we call hardware threads, which is a bit of an abstraction. What it means is that the system can very quickly execute another thread. That's essentially what it means. How many you have, that's up to the designers. You can have 2 or 4, 8 have been around. And, And this is why I'm showing this slide. These threads all get a number that's assigned by the operating system, so you can identify exactly which hardware thread you have in your box. Why do you do that? Well, there was a paper a long time ago that analyzed database behavior back then. Don't know what it was for, doesn't matter. The conclusion was you spend most of your time in the memory system, and now we all laugh at that because we know that. But at that time, that was kind of like, hey, wait a minute. And the idea was, well, you have let's say you got 2 threads executing. The first thread is executing here, then time slices up, the next one comes in, but there's gaps in the execution. You could be waiting for I/O, an expensive cache miss, those kind of things. So it's very natural to have gaps in the execution. And in that paper, they found that in databases, that's where you spend most of your time. You spend most of your time waiting. The idea with hardware threads is that while one thread waits, you transparently, very quickly execute the other thread. And in that way, you improve the throughput, you improve the performance of a single application. It's, by the way, also a big source of confusion, because if you don't have those gaps in your application, you have a very tight algorithm running in the core all the time, extra threads don't help. And then you see papers where people say, oh, I'm disappointed because it doesn't work. And this thing's falling off. Anyway, that's our hardware threads. A little intermezzo. Now back to NUMA. So with NUMA, it's all about where your data is relative to your threads. So we need to talk about data placement. And ever wondered, like, how is the data allocated in your system? Probably not. I hope not, actually. It's not the kind of thing you want to worry about. But what the operating system has, it has a default placement policy. And usually you can change it, but the default is chosen quite well, because that's called first touch. And it's exactly doing what the name suggests. The thread that accesses an element in the page, this is all at the memory page level, accesses an element in that page for the first time, becomes the owner of it. And that's fixed.
Okay.
And that determines the home node of that piece of data. And that's a very important concept to keep in mind, because I'll get back to that. So each piece of data has a home node in the system. And the reason this is the default on all the OSs, it makes perfect sense for a sequential application. If you don't have not a parallel application, you want to have your data close to your memory. So to your thread. So that's the goal of NUMA. Keep threads close to that home node for their data. And here's a simple example. I have a little loop, and I just initialize a vector to 0. That's all that I do. Now, if I don't do anything, there's going to be one thread executing the loop. That's that purple block over there. And by now, you should realize that that means that this is where the data is going to end up. That's what first touch placement policy does. And that may or may not be desirable, but probably in a parallel application, that's not what you want. You probably want to distribute your data across the machine. How do you do that? Well, you can actually leverage first touch to your advantage. And I have to show a little bit of OpenMP here. This is the OpenMP way to say parallelize this loop. And what the OpenMP compiler will do, it will generate the code to actually split that iteration space into sections, and each section will be assigned to a thread. That's how you get your parallelism for a loop like this in OpenMP. Well, that does the magic. Because if I have 4 threads executing that loop, they each get a quarter of that vector. They'll initialize it. That means they own it, because they're the first one to touch that block of memory. And the data is spread out. As simple as it is. Now, of course, real life is usually not as simple as shown here, but that's the basic concept that you have with NUMA tuning. You want to use first touch to your advantage, and that's what I'm doing here. Now, a little bit of OpenMP support. It's not because it's OpenMP, but first of all, it's easy to explain than any other programming model, and I get 10% of a free license.
Oh, wait.
Yes. Oh man, we should talk. I'm an entrepreneur too, Nicholas. So in OpenMP, you get 2 ways to control things at the NUMA level. You get an environment variable, and I put in the name here, but it doesn't matter. With that, you define to the system where you allow your application to run. You can have a really large system, and you can make it as small or as large as you want. Then another variable will map your threads onto those places. Why would you need that? Well, let's say I created 10 places on my system and I only have 4 threads. What do you want me to do? Which of those 10 places should I pick? So that's why you got 2. And with that, you have it all nailed down. You're going to allow it to be run on a certain part of the system or the whole system, and you tell it how to distribute those threads. So those are 2 environments. And just to give you an idea for the kind of choices you have, you can say my finest place is a hardware thread, the ones that I just mentioned, or a core. And a core can have multiple threads, but I don't care which thread you pick in that core. Doesn't matter. You could have LL caches, last level caches. I sort of glossed over that, but there's always a cache last. That's the one that connects to memory. And for some reason, you only want to have the threads, you want to have the cores that connect to that last level cache. You can go a little bit higher. You can go to the NUMA domain. That's one of those nodes that I mentioned. So you're talking about the SMP level. Or you can go to sockets, which is almost sort of no longer relevant these days with the complex architectures that we have. But you get a choice. And you can also support those hardware thread ideas that I mentioned a little while ago. You can have a certain notation because these lists can be very long. So it's very convenient. You can say, I want you to start at number 0. Remember, all those threads had a number. I want 4 threads with an increment of 2 for whatever reason. So in that way, you can completely control where you want things to run. And then you do the mapping onto those places. Okay. And with that, you get a bunch of choices. I'll be quick on it. You can enable it. Yeah, sure. If you trust the system, you should do that. But I wouldn't recommend it. You can disable it. Well, that doesn't make much sense either. So in practice, these are the 3 choices: primary, close, or spread. And for example, close means you want to keep all those threads close for whatever reason. You know characteristics of your application, and you don't want to scatter them out, because with spread, you'll scatter them out over the system. So you need to know something about your application in order to use this with some care. Okay. Now, I try to be honest, but I've been lying a little bit. And this example, and this is why it's so good this talk is early, because nobody's like, oh yeah, sure. So this is what I said. You parallelize the loop, and 4 threads execute loop. That's all true. And then I said the data is spread out. Well, if I was your supervisor, I would ask, how do you know? This is your wishful thinking. This is what you'd like the system to do, but you're dealing with an operating system that definitely has a mind of its own where to put things. So you've got to go a little further, and that's why I brought up all this stuff. Because what you need to do, in this case, you need to tell my places are those 4 NUMA domains, and I want to have those threads spread out. So I want to use all those domains, and in that way, I guarantee that I get what I wanted. No more wishful thinking. So we're almost there, but not yet. But with this, that'll work. And I want to finish with a performance tuning example. And I will go right into what Dan said yesterday. I take an incredibly simple algorithm, multiplying a matrix with a vector. Sure, all of you have seen that, know that. What you do, it's embarrassingly parallel. This is the OpenMP way to do it. But essentially what you're doing the dot product of the row of the matrix times the vector, and that will give you the element. That's what you do. And you do that for all the rows, and you have your final result. Well, as you can see in the picture, these are all independent. I can do the purple and yellow one at the same time. There's no interference, there's no dependency. So this is what we call embarrassingly parallel. Extremely easy to parallelize one line with whatever programming model you use, and there you go. And then you run it. And this is not a typo. It actually gets slower as you add threads. That's not really something to be proud of, but that's what happens. So you take an embarrassingly parallel algorithm, should scale to thousands of threads, and it runs like a dog. What I found, there's an interesting feature about NUMA. I was running this on a 2-socket box, just 2 sockets, and I was suspicious, well, this could be NUMA, because from an algorithm point of view, there's no reason this doesn't scale. And don't read all the text if you don't want to. What Red Hat introduced is actually a way to move data. Instead of in OpenMP, you move threads because that's cheaper. Red Hat can actually move data to where they think it's needed, where Red Hat thinks it's needed. And this is the hacker way of doing it. highly efficient and it works, just don't make a mistake. And this is what I did. And guess what? It's faster. It's faster. At least it doesn't get slower. There's a bit of scalability at the beginning, so that's a freebie. That's like a free lunch. You just enable that feature and it works. But overall, the performance is not very impressive. It stops scaling at 8 threads. And again, remember, this is a highly parallel algorithm. So I don't even get 2x out of this, but again, why waste it? So in this case, you want to enable it. Let's see what's actually happening under the hood. Understanding your CPU, your system. And there's a couple of commands in Linux that are very, very convenient. One of them is lscpu. And what it shows you how your system is structured. I'll do that fairly quickly, but what we see 8 lines here. That means I got 8 NUMA nodes. These are the numbers, 0 to 7. And we see 2 columns with numbers. They have a range. The first column, like 0 to 7, that's 8 numbers, means you got 8 cores per node. That's how you read that output. And the second column here means that you have 2 hardware threads. And those are those numbers that I mentioned in the beginning, and that's why I couldn't skip that slide, because without that initial slide, this wouldn't make much sense. In that way, you can target specifically any thread that you want, hardware thread. There's another command, quite interesting, NUMA control. It does a lot of things, but one of the things is it produces a latency table. And what it's showing you, the distance between those nodes. And it's a relative number.
Yeah.
And first of all, it's a symmetric matrix, better be, because the distance from 0 to 7 should be the same as from 7 to 0. So it's a symmetric matrix, but it's printed in full. On the diagonal, you have the number 10. That's the latency to yourself. So that's like your reference. Mere mortals like me would put 1 there, but the Linux gurus decided 10 is a good number. And actually that's because of Linux scheduling rules. The Linux scheduler was written before all of this came about, and they needed to support it. I wouldn't call it a hack, but it is. And I'm sure they do better at some point, but that's why you see number 10. What you see here is a number, 16 and then 32. That's your relative distance to that other memory. Now, another nice thing about this is not your real latency. This is just an indication. Don't see that as the latency. That's what the warning you get. But what we see 3 numbers. Every row, it's very symmetric, 10, 16, and 32. So what we have here, we have 8 NUMA nodes, we have 8 cores per node, each core has 2 hardware threads, and we have 2 levels of NUMA. I call them 16 and 32. So this is what that system looks like. Seen from a center node, again, the situation is highly symmetric. From a center node, you have 3 remote nodes. Those are the ones with 16. And you have 4 with even a longer distance to memory. So this is NUMA in NUMA. Thank you, hardware architects. I love it. So that's what you get. And this is actually within 1 chip. So here's the detailed thing I just want to show you. So you zoom in on a node, and what you have those 2 threads, and they're numbered in a bit of strange way, seemingly. Like this one is 0, and the next one is not 1, but 64. But actually that makes sense, because if I do 0, 1, 2, 3, I just hop over all those threads. It's just a choice, you just need to know it, and there are ways to find out, as I mentioned. Now, realizing that and not taking that into account, that doesn't sound good. So I go back to my algorithm, and there's nothing wrong with that code. But it's not NUMA aware. And maybe you remember a little while ago I talked about home nodes and where data is. Actually, the disaster happens in the beginning when your data is initialized. And the data initialization in this case was not taking NUMA into account. So I have to go back to the drawing board, because the sequential initialization forces all the data to be on a single node. So I waste my bandwidth to memory. So let's look at a more NUMA-friendly thing. And don't worry, I'm not going to the details of this. I just want to give you a flavor. Here's my original data initialization. I initialize everything that I need. And now I do it the NUMA way, and I add a bunch of OpenMP to it. And essentially what you do reverse engineering. Because when you look at this picture, you know that whoever works on this element needs that row. And you do your reverse engineering and you come up with this, and that will sort of distribute the data the way you like it. Similar to the vector example that I was showing, this is just a little bit more complicated. And I set myself a goal just for the fun of it. I want to run this on my NUMA box, and I want to distribute those threads evenly across the cores and the nodes. And for some reason, at that day, I thought, you know what, I just want to use the first hardware thread of the first 2 cores of all the nodes, these 2, on a specific configuration. And again, this is just illustration. Don't read too much in it. This is my system, and these are the numbers that I want to use. These are the threads that I want to use. I want to equally balance my application over that whole system instead of letting it run. So I take control, and I need to generate the sequence of numbers. And I mentioned those places. This is how you do that. Again, if you don't believe me, just believe me, because this is what it is. And that expands to that, and I get my magic sequence of numbers, and actually when you map that onto what I'm showing here, I get exactly my goal. Let me show one example. In that list, again, this list tells the system where I'd like the application to run, and you see number 0, and the second one expands to 1. So yes, I get 0 and 1 because that's part of this one. So I do get what I want. Then I do some work, I put the binding to close, I run 16 threads, for example, and there we go. And this is what I wanted to show you. This is the performance. The green one is the one with that NUMA feature enabled, the Red Hat feature, so that was the best I could do without changing anything in a way. And this is the one. And just look at the starting point on 1 thread and on 64. Here, this is kind of weird. I never got time to really look into that. Fortunately, I have nobody working for me, so I can't ask somebody else. But it's interesting. That must be the underlying NUMA topology of this system, which is pretty hairy. But if you just look at those 2 points, what you see is now we get a scaling of 34 using 64 threads. Not 64, still like, okay, but certainly significantly better. And if I look at the best score that I had before in 64, and then I look at what I now get, I get an improvement of 22. And all I did was some small changes. And here, this summarizes it, that table. On a single thread, when I don't do anything, I get 5.1 gigaflops in this case. So there's no benefit of the first touch. That's okay, because it's not supposed to be, because I'm not running parallel. Then the second row, 56, was the best I could do with my NUMA trick from Red Hat. I got 8. But my version already got 14 times faster. And then I go all the way to 64, I get more benefit. So altogether, I get a really significant speed up here. And this is the ugly thing about NUMA. I didn't change my algorithm. I only changed the way my data was laid out in the system. And as I said, in applications, that usually happens fairly early on. And there are cases where it's not as simple. I'm going to preempt some questions. There are cases where it's not as simple as this, because this is a static distribution. If it's more dynamic, you're in for a challenge. And but that just shows you how much performance you have wasted in a way by just turning on the box and running your application. And that's why everybody running a data center or managing cloud accounts should hire somebody that can help figure this out, because you'll save yourself tons of money. Final slide. I'm not that frustrated in general, but sometimes I am. And this is a thing. Back in '99, 25 years ago, Lisa Noordergraaf and myself did some experiments on a prototype system that Sun Microsystems was building. And essentially what it did, for static distributions, it solved the NUMA problem. Because the hardware guys and girls, they had designed a board that would count how many remote references you have. They had modified the OS, they tweaked the OS, it would do the counting, and there was a crossover point, like, wait a minute, there are too many remote references, we'll just pull the data over. So that was a very sophisticated thing. That was a prototype, it was running in the labs. It was actually almost productized. And then some magic happened, and with that, the system disappeared. But I wish we'd had it, because, yeah, it won't solve all human problems, but it would certainly have come a long way in many cases. But again, it wasn't meant to be. And with that, I'm going to finish. Thank you for your time. And yeah, I think we can have the Q&A. Well, at least I'll listen to the question. I'm not sure about the answer, but
Interesting.
thank you.
Okay.